Every rational function can be written in expanded form, but this is very straightforward. It just means that the numerator polynomial is in expanded form, and the denominator polynomial is in expanded form. So you can probably guess every rational function could be written in factored form. That just means the numerator is written in factored form, and the denominator is written in factored form. And then we also talked before about how a proper rational function is just one where the degree of the numerator is less than the degree of the denominator, and an improper rational function is one where the degree of the numerator is greater than or equal to the degree of the denominator. When we were doing polynomial division, we said if we've got an improper rational function, then we can write that down in mixed form. And mixed form is a polynomial plus a proper rational function. And here is an example. It's one of those moments in class where we say, we can write exactly the same function in different ways. We can write it down in a factored form. We can write the exact same function down in an expanded form. And here is exactly the same function written down in a mixed form. Are there any questions about that so far? Just a little bit of review. Okay, so this function on the top left, is that a rational function? Yes, it's a ratio of two polynomials. It's a rational function. Is this one a rational function? No, because the square root messes it up, right? The numerator is not a polynomial. Is this a rational function? Yeah, so this is a polynomial. And you can think about it like this polynomial divided by 1. It's the same thing. And the question is 1 a polynomial? It is. It's a really boring degree 0 polynomial. This is a ratio of a degree 3 polynomial divided by a degree 0 polynomial. And so, yeah, this is actually a rational function. And in fact, all polynomials are rational functions for the same reason. This should remind you maybe a little bit about early on in the semester. We were talking about the integers, and this is my set of integers. We said the set of integers belongs to the set of rational numbers. Because if you've got some integer, like the number -6, you could write that down as -6 over 1. And that's a rational number, right? So the integers are part of the rational numbers. In the same way, we could say the polynomials are part of the rational functions, just a subset of the rational functions. Is this one a rational function? No, because the numerator is not a polynomial. Polynomials can only have natural number exponents. Is this a rational function? Yes. Is this a rational function? Yes. Because 75 is a really boring polynomial of degree 0. And so that is technically one of the rational functions. Is this a rational function? No, because I can only have natural number exponents. I can't have x in the exponent. What about this one? Yes. It's a degree 0 polynomial divided by a degree 1 polynomial. So that makes it a rational function. Before I move on, are there any questions? Do I need to clarify anything about that? Thoughts? No? Okay. So let's take a moment to appreciate what I call the big picture. Polynomials are a lot like integers. There's kind of an analogy here, where integers can be represented as a prime factorization. It's kind of like factoring the integer, right? Polynomials can also be factored and written in a factored form. Integers are a set of numbers, and they are closed under addition, subtraction, and multiplication. That means if you add any two integers, you get an integer. If you multiply any two integers, you also get an integer. Polynomials are a set of functions that are closed under addition, subtraction, and multiplication. Because if you multiply any two polynomials, you'll get a polynomial. Integers are not closed under division, because you can divide two integers, like 3 divided by 5, and get a rational number, but it's not an integer, so it's not closed. Polynomials are also not closed under division, because you can divide two polynomials, and sometimes you don't get a polynomial, you just get some other rational function. Rational functions are a lot like rational numbers, in that you might have a proper fraction, an improper fraction, or an integer, if you're talking about rational numbers. But about rational functions, you might have a proper rational function, an improper rational function. And like I said a minute ago, polynomials are actually a subset of the rational functions. Improper fractions could be represented as mixed numbers, where a mixed number is an integer plus a proper fraction. Well, an improper rational function could be represented as a mixed form, where you have a polynomial, which is a lot like an integer, plus a proper rational function. Rational numbers are closed under addition, subtraction, multiplication, and division. And rational functions are also closed under addition, subtraction, multiplication, and division. But just like rational numbers, not every number is a rational number. There's also irrational numbers. And so there's going to be other functions out there that are not necessarily rational functions that we might talk about later in the semester, next math class you take. But this is kind of like the 10,000 foot view, the big idea of what we're talking about in algebra. If you ever hear the word abstract algebra, right? Like if you want to continue taking math classes for any reason, there's a class called abstract algebra that a lot of universities offer. And the idea behind abstract algebra is you just notice the kinds of structures and connections between ideas like this. Abstract algebra is a class that's all about just noticing the similarities and making these kinds of analogies. But this is what mathematicians are thinking in the back of their head whenever we teach an algebra class. And now to move on to your second exercise in your homework. We're going to take rational functions and then rewrite them in other forms. And this is going to be so easy because you've already done this with polynomials. And this time I have a rational function that is in factored form. And I'm trying to first rewrite this in expanded form. And when I want to rewrite this in expanded form, I just have to expand the numerator and expand the denominator separately. And the denominator, as I expand it, you might think about foiling or whatever. This is going to be x squared minus 5x plus 6. Okay. So you expand the numerator, you expand the denominator, and that is expanded form. If I want to rewrite this in mixed form, then I would take the expanded form that I've already found, and then I would do long division, right? Long division is just a technique for rewriting an improper rational function as a mixed form. So we would ask, what times x squared gives me 2x squared? 2. And then 2 times x squared is 2x squared. 2 times negative 5x is negative 10x. And then 2 times 6 is 12. Put down your parentheses and subtract. And we get 0 minus negative 10 as positive 10x. Negative 2 minus 12 is minus 14. And now we're ready to write down the mixed form. We write the quotient plus very good. We write the quotient plus the remainder over the denominator. And just to remind you, we know that we're allowed to stop at this point because the degree of the remainder is less than the degree of the denominator. You can stop doing polynomial long division whenever you see the degree of my remainder is 1, the degree of my denominator is 2, and 1 is less than 2, so I can stop. And this is a polynomial plus an improper, sorry, I misspoke. That's a polynomial plus a proper rational function. And so then I've answered the question. We have the expanded form in blue, and we have the mixed form here in orange. Are there any questions about that? No, this is kind of stuff we've already done, in fact. This question says, write the following function in factored form and in mixed form. And this time, it's given to us in expanded form. To put it in factored form, I just need to factor the numerator and factor the denominator separately, which is good, because we've already done that as polynomials, right? So how does the numerator factor? Yeah. The numerator happens to be a perfect square, so that's just x plus 2 squared, and the denominator factors as 3 times x minus 1. Cool. And that would be factored form. Now to put it in mixed form, it's just another long division question. And I say the question, what times 3x gives x squared? Yeah, 1/3 x. And that way, 1/3 x times 3x gives me 1x squared. And also 1/3 x times negative 3 gives me minus x. Because the 1/3 and the 3's cancel. And then I put down some parentheses and I subtract. X squared minus x squared is 0. 4x minus negative x is 5x. And then you bring down plus 4. Okay. Yeah, so the next question is, what times 3x gives me 5x? I'll write it over here in green. We're saying something times 3x gives me 5x. And so to solve this equation, I could divide both sides by 3x. 5x over 3x. And so that something times 3x should be 5/3. Five thirds times 3x gives me 5x. And then 5/3 times -3 gives me minus 5. And then 4 minus -5 is 9, and that's going to be my remainder. I can stop now because my remainder has a degree of 0, and that's less than my denominator, which has a degree of 1. And so to write my mixed form, I write the quotient plus my remainder over my denominator. And that gives me the mixed form I was looking for. Any questions here? Okay. One more similar kind of question. Says, I want to take this rational function, and this time it's given to me in a mixed form, where I've got this linear polynomial plus this proper rational function. And I want to rewrite that in expanded form and in factored form. So let's do expanded form first. And the trick here is that we are going to find a common denominator. And to find a common denominator, you have to think about multiplying everything times x squared minus 9 over x squared minus 9. And then the common denominator is going to be x squared minus 9. Whenever I take x times x squared minus 9, I'm going to get x cubed minus 9x. 4 times x squared minus 9 is going to be plus 4x squared minus 36. And then I have plus 2x plus 26. Because that was already divided by x squared minus 9. And then, this is almost there, we just have to collect like terms and put everything in the proper order. And so my numerator is going to be x cubed then for the x's, I've got -9 plus 2, so -7. And for the constants, I'll have -10. Yeah. This is in expanded form. Okay, the last step is I need to write this in factored form. To write it in factored form, we're going to start from what we already have for expanded form. And then I have to factor the numerator and factor the denominator. And the denominator is easy to factor. Yeah, x plus 3 times x minus 3. And that's good for the denominator. The numerator is a cubic polynomial, though, and I can't just use the old school factoring stuff. I can't just use a quadratic formula. I have to use the rational root theorem when I have a cubic. And the rational root theorem says everything that could be a root is going to look like factors of 10 divided by factors of 1. So that's going to be 1, 2, 5, and 10. But also negative 1, negative 2, negative 5, and negative 10. This is what we're going to try out for potential roots. So I'm going to set up a little synthetic substitution. And the coefficients of my polynomial are 1, 4, negative 7, negative 10. I bring down the 1. And what's the first number we should try here? 5? Okay. Let's try out 5. 1 times 5 is 5. Plus 4 is 9. Times 5 is 45. Plus negative 7 is 38. 38 times 5 is a big number, and so this is not 0. Negative 2? Okay. Yeah, we are just guessing, so there's not one that's better than another. Negative 2, bring down the 1. 1 times negative 2 is negative 2, plus 4 is 2. Times negative 2 is negative 4, plus negative 7 is 11, times negative 2 is 22. Oop, so that's not 0 either. Remember, we're looking to make that box a 0 in the bottom right. That's how we know we found a root. I try positive 2? Okay. Bring down the 1. 1 times 2 is 2, plus 4 is 6, times 2 is 12, plus negative 7 is 5, times 2 is 10, and that does it. So we know 2 is a root of the numerator. And that means I can go ahead and rewrite my numerator as x minus 2 times, what goes in here? Do you remember?
X squared plus 6x plus 5.
Perfect. So you get the coefficients of your quotient just by looking at these numbers. All right, so it's not in completely factored form yet. To finish factoring this, I would have to factor the quadratic part. And how does that quadratic part factor?
X minus 5 minus 1.
I think it's x plus
Plus
1 and x
plus 5.
plus 5, yeah. There we go. And that is factored form. You did it. Any questions about what we did here? Either with the expanding part or the factoring part? All right, so to sum up really quick, we can write things, we can write rational functions in 3 different forms, right? It could be in expanded form, in a mixed form, if it's an improper rational function, or a factored form. If you want to go from factored form to expanded form, you just have to multiply all the factors together. And that is kind of a hassle, but it's pretty easy. Going from expanded form to mixed form, we do long division. When we want to go from mixed form to expanded form, we just find a common denominator. And add those up. And then to go from expanded form to factored form, we have to factor, which might mean, you know, factoring in your head, or it might mean factoring with the quadratic formula, or it might mean having to factor with the rational root theorem. But this is the idea. It's not really possible to go from factored form to mixed form, right? There's no strategy that gives you a shortcut, and there's no shortcut to go from mixed form to factored form. You just have to go through expanded form to make that happen. So, a rational equation is an equation where all of the terms in the equation are rational functions. We call them rational expressions. And we want to find all solutions to this equation. So here we go. I've got 3 divided by x plus 3 equals 5 over 2x plus 6 plus 1 over x minus 2. Step number 1 is going to be factor the denominators. You don't have to worry about factoring the numerators if there was anything to factor. But we always think for a moment, can I factor the denominators? That would be step 1. And this is very easy in this case. It's not always so easy, but in this case, yeah. The only denominator that could be factored is this one, and this would factor as 2 times x plus 3. Okay, step number 2 is going to be multiply the whole equation by all of the denominators. So I multiply the left side and the right side by every single one of the denominators that I see, right? I'm going to multiply by x plus 3, and I'm going to multiply by 2, and I'm going to multiply by x minus 2. When I'm done multiplying, this first term is going to be 3 times 2 times x minus 2. And when I multiply that first term times x plus 3, it's just going to cancel out with x plus 3 it already has in the denominator. The next term is going to become 5 times x minus 2. Because when I multiply by x plus 3 and 2, it cancels out with the denominator. And then the last term becomes 1 times 2 times x plus 3. Does that step make sense? All right, so now I just have to expand both sides. I'm just going to distribute everything, right? So 6x minus 12, 5x minus 10, and 2x plus 6. Now I have a linear equation. And linear equations are pretty easy to solve. We just want to collect like terms. I would probably want to collect all of the x terms on the left side of the equation, collect all of the constant terms on the right side of the equation. And so that looks like saying minus 7x on both sides and plus 12 on both sides. So on the left side, I get minus 1x, and on the right side, I would get negative 10 plus 6 plus 12, which is 8. And then that tells me x is equal to negative 8. So to recap, step 1, anytime you see a denominator that could be factored, go ahead and factor it. Step 2, multiply the whole equation, left side and right side, by every denominator. And then you expand everything out, you collect like terms, and in this case we had a linear equation, so that was pretty easy to solve. Questions? Concerns? Nothing? All right, raise your hand, let me know if you're wondering or feeling confused about anything as we go along here. This one says, find all solutions to the following equation. Let's see how this one goes. Step number 1, I want to factor the denominators. So as I rewrite this, I'm going to factor the denominators. How does this last denominator factor as? X plus 2 and x minus 4. The next step is I'm going to multiply the whole equation by every denominator. So multiply by x minus 4, multiply by x plus 2, and I get x plus 2 minus 5 times x minus 4 equals 6. Of course, this is x minus 5x, so negative 4x. 2 plus 20, right? Because negative 5 times negative 4 gives me positive 20, so 2 plus 20 is 22. And then subtract 22 from both sides. 6 minus 22 is negative 16. And if I divide both sides by a negative 4, x equals 4. These questions in the last two examples were pretty easy because after I finished factoring the denominators and multiplying by the denominators, I had a linear equation. That's pretty easy. In the next couple of examples, we'll do one where we end up with a quadratic equation, and then one where we end up with a cubic equation. So these next two examples are going to take a little bit longer, a little bit more tricky. Find all solutions. So I want to factor the denominators. Step number 1. How does this denominator factor? Very good. X minus 3x plus 3. And then I want to multiply the whole thing times every denominator, so x minus 3 and x plus 3. Then the first term becomes 2x times x plus 3. The next term becomes 6 times x minus 3. And then that is equal to negative 28. Distributing and expanding everything gives me 2x squared plus 6x plus 6x minus 18 equals negative 28. And now I want to move everything to the left-hand side and collect like terms. I say that because that last line, I can tell that it's a quadratic equation. And the way we always solve quadratic equations is we move everything to the left-hand side so we can make the right-hand side equal to 0. And so that means I add 28 to both sides. And I'll get 2x squared plus 12x plus 10. Before I try to factor the left side, can I make it easier on myself? I could divide by 2 and get x squared plus 6x plus 5 equals 0. And then now how does that left-hand side factor? x plus 5 times x plus 1. And that means my two solutions to this equation are
-5.
perfect, -5 and -1. So this one, as an example, was only slightly more difficult. It starts out the same way. It starts out, we try to factor the denominators, we try to multiply the whole thing by all the denominators. We still expand, distribute everything. What made this only slightly more difficult is that we had a quadratic equation, and so we had to move everything to the left side, and then we had to factor it instead of just a linear equation. Okay. No questions? So I've got one more example for you today. Let's see. There's nothing to factor in the denominator here, right? So what I could do is jump straight into multiplying the whole equation times x plus 1 and x plus 3. And when I multiply, this first term is going to be x times x plus 1 times x plus 3. The second term is going to be 6 times x plus 3. And then this is 8 times x plus 1 times x plus 3. And this is very good. X plus 1 times x plus 3 is going to be x squared plus 4x plus 3. And then I multiply by an extra little x. So that's what I'll end up with for the first part. This is 6. 4 times 8 is 32. And then 4 times 3 is 24. And then minus 16x minus 16. All right. I want to move everything to the left side of this equation because I can tell this is a cubic equation, and so the only way to solve it is to make the right-hand side equal to 0, make the left-hand side equal to some cubic polynomial, and then we factor the polynomial. So on the left-hand side, I'm going to have x cubed. For my x squared terms, I'm going to have 4x squared minus 8x squared, which is negative 4x squared. For my x terms, I've got 9x on the left side and 16x on the right side, because it's 32x minus 16. So 9 minus 16 is going to be minus 7x. On the right side, my constants are 24 minus 16, so I've got 8. On the left side, I've got 18. So 18 minus 8 is 10. Okay, the last part is just going to say, how do I find the roots of this cubic polynomial? I have to use the rational root theorem, yeah. And so this is factors of 10 over 1. 1. And I'm going to set up a little synthetic substitution. This time my coefficients are 1, negative 4, negative 7, and 10. What should I try first? 2. Okay. Bring down the 1. 1 times 2 is 2, plus negative 4 is negative 2, times 2 is negative 4, plus negative 7 is negative 11, times 2 is negative 22, and that's not 0, so I can scratch that one off. What do I try next? Negative 1. So I bring down the 1 times negative 1 plus negative 4 times negative 1 plus negative 7 times negative 1 plus 10 is not 0. So not negative 1. Negative 2. All right, let's try negative 2. Bring down the 1 times negative 2 plus negative 4 times negative 2 plus negative 7 times negative 2, and that works. So one of my roots is negative 2, and I can take this equation and rewrite it as x plus 2
X squared minus 6x plus 5.
Very good.
That's x minus 5 minus 1.
Okay, so I've got 3 solutions. Negative 2, 1, and 5. All right, so that is the trickiest example of all because we had to start with the rational equation. We multiplied by the denominators, expanded everything out. Moved everything to the left side because we noticed that it was a cubic equation. We used the rational root theorem to try out some things until we found a root. And then we factored and we factored and we